Okay, another day, another subject. As many of you know, don't answer it. As many as you know, I just had someone ring on the door. That's why we were startled. Just where we start the day. As many as you know, we have a conference going on in Buenos Aires, Argentina on the 10th of November. Let me put this up there here for a second. There we go. See if I can move aside, make it a little bigger. And it's a physics conference, the 6th Rational Physics Conference. We've had several now in different countries. This is going to be on the 10th of November. And, you should be, if you're planning on participating, you should include you should send your report, your abstract or whatever, your article to the Rational Scientific Method or to the, there's a special site for the 6th Rational Physics Conference. So either one, sign up for those. And it's a good idea to start writing your articles, by around now, at least get an idea what you want to talk about and get the points that you want to talk about and write them down and start writing. What am I going to talk about? Well, I'm going to be talking about polarization. So there you have it. Now it's no more a secret. And I'll even do better on that. I'll put something here today that'll tell you what I'm going to talk about, specifically what I think or how I think polarization happens. What is the mechanism of polarization? And that's what I want to talk about today as an introduction. And so many of you might ask, if you're not familiar with the subject, you might say, but what is polarization? And so here I have a little diagram, that little picture here that, let me move aside so it doesn't hit me in the face, that shows you graphically what polarization is about. This was discovered already in the 18th century. And essentially what happens is you shine a light, and that light goes through what is called calcspar, Iceland spar, I think it's also known as that. And
what's the calcspar made of?
I don't know exactly what it's made of. It's like carbon, some carbon compound. But the issue is that all these atoms or molecules that comprise the calcspar are oriented. They're in arrays, and so they have the ability to just according, well, I'll get to that in a second. Here you see it here in the picture, but essentially, if you can see there, the what is that? The vertical polarizer. It allows only the vertical components of light to go through. That's the explanation. So essentially, I have an explanation of what polarization is at the same time that I'm also giving you an idea of what the establishment says causes polarization. And the main thing here is that, you send a wave, an electromagnetic wave. Electromagnetic has an electric field and a magnetic field. And what the polarizer does, apparently, or that's the explanation, is that it allows the vertical component to go through. And usually they do this with the electric field. Okay, so they allow the electric field to go through, and I guess the magnetic field to stay back because it's blocked by the vertical bars of the calcspar. And what this means is that light that you see there, the between the two polarizers, is comprised solely of the electric field. Here we have light that apparently, if we accept the official version, right, only has an electric field. There's no magnetic field. And, we always thought that that's what's called an electromagnetic field. And that's what James Maxwell showed, that, you know, light consists of two mutually perpendicular fields. And here they're saying they're going to block one of the fields out, essentially, you know, because I'm not sure how they explain that on the other side of that, or between the two polarizers, that you're going to get the horizontal component, which is part of the electromagnetic field. So again, you know, it's that's the explanation. That's what they have with wave. And there's even a more fundamental objection from me at least to that, in that there is no such thing as a wave. We have to identify what physical object mediates light. And by saying wave, you're not telling me what is waving, because wave is a verb. And what they've done is, like, you know, infinite, they turn into infinity. Well, they turn wave from a noun, from a verb into a noun. And that's what they use today, this verb, which is a noun. Anyways, that's the wave version. And you might say, well, I thought quantum was king, you know? Quantum is a particle theory. In other words, it's based on the particle hypothesis, that everything is mediated by particles. And particles and waves don't get along very well, okay? And so here's the version, here's the, well, first here's the wave version in a different format. You have a picket fence analogy. You have the vertical picket fence, and you have the horizontal picket fence. And, you know, light comes in there as a both magnetic and electric wave. And then the component that goes through apparently is the electric field or magnetic field, one of those two, but not both. And then when you put a horizontal polarizer, it extinguishes the beam altogether. You will not see it on the screen behind the second polarizer. And so that's what they've shown with polarization, that it has the property of extinguishing the beam. Okay? And again, they use the wave, and the question is whether that wave, that piece of the wave, that portion of the wave that's between the two polarizers, whether that consists only of an electric field. And again, what is a wave? But let's move on to quantum. Quantum's, you know, how do you do this with particles? If quantum is a particle theory, there you have it with particles. You have all these red particles, right? In this case, photons, right? And, you know, you can't explain. The particles would just go right through both polarizers. You know, in fact, the second one is usually called the analyzer. So you have the polarizer and the analyzer, and particles just go through there. What would stop them? And there's only a one-liner in the Wikipedia that mentions quantum mechanics, particles, very, very timidly. And I copied it so that you can see how quantum is not involved in this, and that's why I don't hear much about polarization. Let me make it a little bigger here. It says, in the quantum mechanical view, light is composed of photons, particles, right? Polarization is a manifestation of the intrinsic angular momentum, the spin of the photon. Oh, okay, that's nice to know. More specifically, in quantum mechanics, the direction of spin of a photon is tied to the handedness of the circularly polarized light, and the spin of a beam of photons. You know, you take the whole beam now, you're talking about not individual photons, but the whole beam, you start twirling it around. In other words, you spin it. And they say that the spin of a beam of photons is similar to the spin of a beam of particles, such as electrons. That's all they say. That's it. That's all you'll find in there. My son told me a minute ago that he can't find any questions in Quora regarding polarization.
Well, I just typed it in Quora, polarization, just a word, and no questions came up.
Uh-huh.
But you think it was...
Well, yeah, I guess it's not about polar bears, and it's not about, you know, the polar ice caps melting.
Yeah, if you just type in polar, you get that.
So, you know, nobody deals with polarization because it destroys quantum mechanics. Quantum mechanics has no way of answering polarization. So in college, they'll teach you that, well, they'll use the wave. And you say, well, where's the wave in the standard model? You don't see a wave there. And that's the only way they can explain it, through a wave. And then they put this thing in there saying spin. But you're not explaining the mechanism. Spin, I don't care which way the particle is spinning. They should all go through both polarizers, onto the screen. Why would the screen stop one spinning particle and not the other spinning particle? If they're both particles, if they're zero-dimensional particles, who cares in which way they're spinning? Or please explain in what way the spin of a particle is stopped or is prevented from going through by the polarizers, by the calcspar. And again, there is no explanation under quantum mechanics for sure. And under the wave model, well, there's too many problems, fundamental problems. Wave is not a physical object. You got to tell me what object is moving in there. That's first one. And the second one is that even if you allow for the wave, if you can see that it's some kind of weird object or mediator, if you allow only the electric component through, what happens to the magnetic component? Are we saying that light consists only of an electric field, no more of an electric and magnetic field? So there's too many problems with the official explanation. That's why you won't find much information. You'll find a lot of math, but you won't find a physical interpretation for polarization. Not one you can live with. And I'm going to write about this for the conference, and you're the first ones to hear it. You're going to hear a theory today, my theory. You can steal it because you heard it here. You say, hey, I'm going to take that. If you like it, maybe you don't like it, fine. And I'm going to do it with a rope model of light. Now, I've written about polarization 100 years ago, and I proposed a mechanism. And the mechanism I'm not too satisfied with even today, so I began to think about this again, and I've got a different mechanism now that defeats or debunks my previous theory. So that's what happens when you think too much about these things. My explanation was, and you can find it in my paper, published paper, that when you move the back polarizer, let's do it here. You got a front. Well, let me remove the stuff because I'm going to get into my own thing. So you've got one polarizer and you got the other polarizer behind it, right? And what I'm saying is when they're both up and down vertical, all the ropes go through from atom to atom. Remember, all atoms are interconnected under the rope model. But what happens when you turn one around? The analyzer, the second polarizer. Well, the beam is extinguished, and the question that the way I came up with a theory was that all the atoms here are connected to, just look at the top of my finger here, the FU finger, right? If this is connected to this one, well, the beam now is going sideways because you move that one over. And then that same atom is connected to the screen, right? And so what you're doing is diverting the beam. Not diverting the beam, but what you're doing is doing a refraction. Okay, light is now diverted in a different direction. The main part of the beam is diverted. Okay, and that was my original explanation. And I've got it. Picture's worth 1,000 words. You can look it up in the article that I wrote, and you'll see a picture, and then you'll understand what I'm saying probably a little bit better. But now I've got a different theory, and I think I like this one a little better after thinking about it a little more. And let me show it first, then I'll see if I can model it with a little rope that I've got here. And so it goes something like this. Oh, well, I forgot one interesting point, and that's that when you do the picket fence analogy, you have one. Let me put that one back up there. Where is it? Here's the picket fence, right? Well, the first part of the beam that reaches the first analyzer, polarizer, it's got all the components, electric and magnetic field. The vertical picket fence only allows the vertical component of light to go through, and the horizontal polarizer extinguishes the beam altogether, so you don't see any light on the screen. What happens is, if you happen to put a third polarizer in between them at 45 degrees, the beam is reestablished. See? So now you've got the beam coming in until it reaches if it is to reach the second polarizer, it's going to be extinguished because the horizontal component kills it, right? But if you put in between a 45-degree polarizer, that's another polarizer just like the others, but you put it at 45 degree, it reestablishes the beam and you can see it on the screen magically. And of course you can't explain none of that with particles. There's no way. And they don't. They don't. That's a subject that, you know, in college people simply accept the wave very loosely, and they say, oh, okay, it was explained. Okay, yeah, fine, picket fence. And what I'm saying is, you know, this we've got a better explanation for this. So let me get these out of the way, and I'm going to put my rope model here. Let's see, it's kind of small, so well, let me see if I can move a little bit out of the way. Make it a little bigger there. And I don't know if you can see the rope there very well, but we've got a red and blue rope, okay? In other words, the threads, I color coded them red and blue so that we can see them a little better. And you see where the arrows are there? What that's pointing to, and the arrows are blue, is that in both cases, the blue part of the thread, or the thread that is blue, is on top, and the red one is on the bottom. That's what I want to show you.
The part that's touching the atom?
Yeah, the one immediately coming out of the atom, right there. And maybe I should do it with a rope. Look, a little bigger, maybe it's easier to see. Okay, and I'll have to get a chunk of this because I guess the whole rope doesn't fit on the screen. You can see here. Let's see here. Here we go. On the two ends where my fingers are, in my two hands. It's the other way around here. You can see the blue thread is on top in both cases. Okay. And that's what I'm showing there. I'm showing that the blue thread is on top and the red one is in both cases at the bottom, okay? Okay, is that clear? So we have the blue thread on top in both cases, and if we put another polarizer, vertical polarizer, the beam goes through and you see it on the screen. Okay, so in this case, we have just vertical polarizers and they just transmit the signal to the screen. Why? Because under the rope model, you know, you have to understand that all atoms are interconnected and they relay the message through the rope from atom to atom. Okay, so what they're doing here, they're both with a blue thread on top where it touches the atom, so it's the same thread, right? The atom is just relaying the signal that it receives to the next atom down and so on down the line all the way to the screen. What happens when we turn the polarizer around? The second polarizer, no, wrong one. Where is it? I lost it. Ah, I lost it. Here it is. No, that's still the wrong one. Well, I guess I missed one here. Did I do this right? Well, this is the wrong one. I just copied the same one 2 times, so I made a boo-boo here. But I can still explain it with this one. Just forget about that. Oh, that's such a shame because I put the wrong one up there, and I don't have it here. I put the same one twice. Anyways, this is the issue. The issue is that if the second polarizer is in a horizontal manner, the beam is completely extinguished. Okay, why is it? Well, because you have, at that point, what you've done is you had blue on top and blue on top at both ends. But now you're going to rotate this guy, right? And now you're going to have red on top, okay? Okay, so you start out with blue and you end up with red. You end up with the other thread, in other words. That's what I'm saying. And so you did that just by twisting the polarizer at 90 degrees. So now you have the other thread on top, and it's like what you see in the slit experiment, where you have constructive and destructive interference. You have destructive interference when you have, one comes with a red to the screen. I'll call it that one there. Let's see if I can see it, show it there. And the other one comes, with the blue one on there. There we go. That one. I gotta work on my mirror image here. Red, and the other one comes out blue. And what happens is, the beams cancel each other out. There's destructive interference when the red thread, I'll use red and blue because it's easier to talk about that. If you have the red thread hitting the blue thread, you get destructive interference. If you have two blue or two red, you get constructive interference. Well, this is something similar. As soon as you rotate that polarizer, right, you twist it, what you're doing is rotating the point at which the thread is, or the two threads are meeting the next atom. And it's rotated exactly, 90 degrees from the starting point. And that's why the beam is not, these atoms are vibrating, they're sending signals to each other, and this guy now is not sending the same signal it's receiving because you've twisted the atom sideways. And that's what the polarizer can do, because calcspar, all the molecules are oriented in an array. They're all organized very well. What happens when, like in this case, we're putting a 45-degree polarizer in between? Well, now you have the situation where, and this is the best way to show it because I can't even draw this. If someone can draw this better, I really appreciate it. I'm going to put it like that so you can see that the red and the blue are essentially side by side at that point. Okay? So they start out with blue on top. They ended up with red on top. But now we're talking about the fact that you put a polarizer at 45 degrees and they're sideways. What is called, you've probably heard of a quarter wave plate. That's what it does. It bends the rope. They call it the wave, but it bends the rope a quarter wave. Quarter of a wave is shifted sideways. And that's what it is. Now you have these sideways, okay? So now from the atom in the polarizer, in the first polarizer, to that second atom, there's only half a twist. And both red and blue get there. And from there, red and blue go to the other atom. And again, the other atom is receiving blue on top. So the beam is again brought up to life. And you see it again on the screen. That's how the magic is performed. That's what I'm proposing anyways. Obviously, it'd be nice if someone else also, brings up or studies polarization and comes up with a better theory. But I think I like this theory. This is a theory I can live with. I'm saying that the rope, by its very nature, and again, it fits completely with a lot of the wave explanations they've given for 200 years now, and that's that, now we can see why, from a physical point of view, why if the blue thread is on top in both cases, you have constructive interference, like in the case of the slit experiment. When you have the red one on top on the other end, now you have destructive interference. They both cancel out. And if you have someone in between that, puts the threads side by side, then that changes what the receiving atom will experience, when the two threads arrive at it. And that's why the beam is again reestablished. Okay? So that's my explanation. okay, for polarization. I leave it up to other people to bring other theories on polarization, but it is interesting that, in my opinion, that polarization really defeats quantum mechanics, because quantum mechanics cannot answer it under no circumstances with particles. And with that, we begin our day with my son here asking questions.
On to the questions, Ron.
Okay.
Well, earlier you were talking about how you updated your theory.
Yeah.
And you're constantly updating your theories. So the question is, which theory of your own or detail of a theory are you still not satisfied with? Of not that one, but other theory. Like which rabbit holes do you have yet to go down?
I disagree with all my theories. I'm my worst critic, I guess. I constantly revise theories. I look at them and say, well, is this what my interpretation really is? This, can I live with this? And I found errors in fact, in the book Why God Doesn't Exist. One of the errors I've admitted to already, so people keep beating me up whenever they come up to it, and I say, I've already admitted, I've confessed, I've served my time, please forgive me, I'm not on probation anymore, so, and what it is that, in the book, I put space as a concept, as a separate concept, as a special kind of concept, and I said there's objects, there's concepts, and there's space, and I repent. I ask for forgiveness. Space is nothing, is a synonym of nothing. Nothing is just a concept that we created. The reason I got fooled, and just so in case you don't want to make the same error, I said, space was there before we came along. And it turns out space is not there. Okay, there is nothing there. There's only matter out there. And space is something that because we see this contrast, we designate and call that thing, that black thing that surrounds the moon, we call it space. There is no such thing as space. There's only the moon. And it's very hard to understand that because we think that everything is an object, that we live in some kind of balloon, that the universe is, some kind of balloon. We talk about, is the universe infinite? Is it finite? Neither one. Space does not exist. There's no such thing as space. Space is nothing. It doesn't have frontiers. It doesn't have borders. It doesn't have boundaries. So not even God, Almighty God, as powerful as He is, He cannot cross space because there's nothing to cross. Well, literally.
I think the temptation comes from there always being some sort of medium, like fish in water or birds in air. There's always something there. Yeah,
and that's true. Fish are in water, birds are in air, and so we think that everything has to be in some kind of medium, because that medium is providing the contrast, the background. It's the stage. And no, space is not a stage, and it's very hard to get away from that thought. It's very hard to come to grips with that. There is no such thing as space. Space is vacuum, total vacuum. There's nothing there. Matter moves with respect to matter, and it does not move with respect to absolute or to relative space. Either one. There's no such thing as space. Space is nothing. And it tricked me also because I put it in the book. So I wrote it, and I repent.
Which theories are you grappling with now?
Well, the extinction theory is one which I constantly revise.
Or which details?
The little details of how we're going to get to extinction, how we're going to become extinct, how the step by step. I want to visualize each step and find out, if there's something I missed, or if there's a better explanation of how the economy is going to fall apart. Essentially, I'm saying that there's going to be an economic collapse. What that means to me is that money is going to be no more. And because money is no more, because no one believes in money, no one accepts money anymore for whatever reason, right? But that's what I'm saying. If money is no more, then there's no incentive to go to work or to produce by the suppliers. And there's nothing to buy things with because, people have money, but nobody accepts it. So all we have is paper or a number in a bank on the internet somewhere in a bank account. So that's what I think is going to happen, and that's what I call an economic collapse. Okay.
I was thinking more along the lines of physics, but that's okay.
Well, okay, but in the case of physics, there's many subjects. Like, there's so many ramifications. What I do work on constantly and go back and check my work and check my steps to see I did them correctly are definitions. I want to make sure that the definitions are solid. And so when someone challenges my definitions, for me it's an opportunity. It really is, in part because, not because I will accept what the other guy says, maybe his criticism is off the mark, but the question is, how do I explain to that person, why I have that definition? And that's makes you think and keeps your brain running. You have to try to explain why you have that definition, why it's important, how it's related to the others, and you build this solid foundation. And it's the only way you can get your theory across, or your entire foundation across. One word has to be related to the other. Like, I define. In fact, this morning I did that. You define words in a certain order. You can't define them in any order. You need the word object first, then you need to find out what the separation between them is. We call that distance, and then we have the set of distances, that's location, and then a couple of locations or more, that's motion. And you have to have it in that order. You can't define motion unless you define what an object is, because you can't do motion without objects, I think, at least in my rationality, or my world of rationality, you absolutely need to have objects to do motion. And and you might say, well, that's obvious. No, it's not obvious. Believe me. I have a friend who told me once that motion is what constructs objects. That's what he was taught in college. He's got at least a bachelor's degree. So he was taught in college that matter is made of motion. So no, it's not obvious. If you thought it was obvious, it's not.
I get the feeling that nothing's obvious in physics.
No, you really have to pin all these things down, because you'll be surprised what people believe out there, or the thoughts they have. And it shocks you sometimes, because like, one thing that shocks me all the time, okay, that I'm saying you need an object to do motion. But if you have, again, and here I always have my two little balls. You have two objects, two balls. I'm off center today. You have two balls. This one influences this one, okay? Somehow it makes it move. I move this one like that, and this one moves like that. So I move this one up and down, this one moves up and down. So this one's somehow related to that one. To me, something I didn't have to go to college, or I was born with it. There has to be a mediator. There's no way you can tell me that this one moves that one and there's nothing in between. Absolutely nothing. You got to put something in there. Put spirits if you want, fine. I don't care. But you better put something in there, because otherwise you're doing magic. And to some people, that's not, intuitive. It's not natural to them. They say, why do you need an object? What do you mean? I'd have to explain that to you, that you need an object between these two objects for this one to influence this one. And this is just blows my mind that people absolutely need to have this explained to them, or that you even need to argue this issue with them. And so you got to be careful with your definitions, and don't take anything for granted, because you'll be surprised what's out there.
Well, I typed in physics in Quora, and the question that came up the most is, in different forms, what is the best book for learning physics? And it's usually always followed up by for X exam, or for the 12th grade, for the 10th grade. Why
God Doesn't Exist. That's the best book.
That's the plug.
Yeah, in fact, I think I answered that question. Look it up. Probably you'll find that I answered that question. It's the best book in town. At least I'm not saying it's the best book. I don't like to brag about that. I'm just saying that it's a book that will give you a different point of view. And so if you want to challenge your mind, if you are a person who is intellectually inclined and you just want to stimulate your mind, even if you don't accept the theory, is beside the point. But if you want to stimulate your mind, that book will stimulate your mind. It'll give you a different universe that you probably never heard of or never thought about. And so we have the universe where God and his angels runs it, and we have the other universe where quantum mechanics and general relativity and maybe even string theory run it. And then you have the rope model, which is a totally different universe, says all atoms are interconnected and space is nothing. And so, yeah, you have a little different universe in the one that I'm explaining in there, and I go from the atom all the way to light and the universe. So you get a pretty good picture. Whether you accept it or not, again, it stimulates your mind.
But you'll fail all your tests.
Yeah, fortunately, I went to college before coming up with all this, because if I would have gone to college at the age of 20 with all the stuff that I came up with later on, I would have flunked every test, and I wouldn't have gotten a degree. That's simply the way it is. These things are not. And another fellow who's like that is my dear friend, the Tasmanian devil, Stephen Crothers. He studied late in life, and I think that's got a lot to do with why he and I, both of us, criticize the establishment. We were not really brainwashed when we were freshmen, or when you're still soft, and you come into college very naively and say, well, I'm going to learn physics, or in my case engineering, and I'm going to study, and I'm going to be the best, and then you run into professors who know a lot more than you, or at least know the arguments, how to destroy your arguments, and even if you have different ideas, they put them to rest right there and then. Either you fall in line and accept what they're telling you, or you don't pass the test and you don't have a career. That's one issue. But you could still, be in, a silent dissenter. But then when you get your degree, you can't go out there and say, I don't believe in general relativity or quantum mechanics. You can't say that. Who's going to hire you? Who's going to recommend you? Are you going to work at CERN if you don't believe in quantum mechanics? What are you accelerating? Are you going to work at are you going to work at Cambridge? Are you going to work there as a theoretical physicist and you don't believe in the Big Bang? What the hell? What are you talking about? So no, you got to fall in line.
That ties into my next question,
okay,
which is one of the questions in Quora. What can I contribute to science and research if I have an average IQ? Was the rest
Forget about the IQ. Anybody can contribute. Sometimes even the stupidest person comes up with a good idea. So I don't care. Sometimes I don't care what the IQ is. Let's see what your theory is.
Let's shorten the question to what can I contribute to science and research?
Yeah, and
like if someone does study it or really get into the issue, what could they add?
Today we're more into technology, so when people graduate, they don't really do thinking. Very few people go in there into thinking research. Most people go out there and just get a job, and they work in some company and they do something. If they're engineers, or physicists, physicists maybe work at NASA, maybe building rockets or whatever, or accelerating so-called particles at the accelerators. They get involved in those things. Now, how many of those really sit down and do some armchair stuff at home and think about the universe? I don't know. I think there's not that many. And 99.99% of them, they do it based using quantum mechanics and whatever they learn in college, general relativity, string theory maybe, as a foundation. So it's not like they think out of the box. I heard this, there's this lady who works at CERN, and I didn't hear it directly from her mouth, but she said it through someone else, that she doesn't believe in quantum mechanics. And she's working at CERN. So she doesn't believe a lot of this stuff that they're doing, but it's her job, and I better keep my mouth shut if I want to keep it, if I want a career, that kind of thing. And so it might surprise you. Maybe some people are out there, they're skeptical, but they say, well, I got to keep doing what I'm doing because otherwise I won't have a job. That's one issue. And the other one is, what do you propose in exchange? And again, a lot of these people don't have anything to propose in exchange, even though their intuition says something is wrong here, but what are they proposing in exchange? So that's the other issue, yeah.
We got a question from Dan.
Uh-huh.
Does the thread/rope exist by definition?
The thread and rope and the word exist. I think I mentioned that in a previous video, Dan. They're kind of there's a contradiction there, and the contradiction is that when we look at the word exist, we have always applied it to atoms and above. You can maybe talk about subatomic particles, fine, but you're always talking about particles. Something that is thicker or bigger than the rope itself. So we never talked about, that's why they call it energy. Light is energy, because they don't know what that thing is. They don't know what that energy is. And so they never said, well, what is the thickness of energy? What is the width of energy? How big is energy? You don't have those questions because it's energy, and it's a fuzzy, you got to think of it as some kind of spirit or maybe smoke-like entity, that's what you got to think about it as. And so nobody thought of light as being mediated by a thing such as a rope. Now, even if you model it with particles, you say, well, how thick is the particle? Well, that's why they made it zero-dimensional. A photon is a point particle, zero-dimensional. They don't look at structure. They say, you want me to draw a photon? Here's a photon. That's a photon. Is it really a circle? Is it really a ball? Well, no. We don't know what it looks like, but that's what we model it with. So again, we don't know what light is. They never proposed any real entity for light. So all that the word exists has always been related to atoms and above, really. We can say that the table exists. We can say that, the dog exists or whatever, the house exists. And when you get down into the little things, well, you can say the atom exists, okay? Now, do muons exist? Well, they say, yeah, they exist. But we don't know what that word means. And so once we define the word in a scientific manner, and we say, look, I'm going to define exist in such a way that it can be used consistently, rationally, scientifically, and it's an object that has location. Well, that applies to atoms. Now, does that apply to the rope or to the thread? And let's forget about the thread, really. Let's talk about the rope. Rope is light. Light is rope. Rope is the mediator of light. That's the theory, right? Or that's the proposal, the hypothesis. And the question is, we've never talked about, does the rope have location? Location with respect to what? With respect to another rope that's parallel to it? Like, are we saying that here we have 4 atoms, right? They're connected by ropes. They're in parallel, okay? Like in the case of that I just touched there, the calc spar, okay? So the ropes are straight, right? And the atoms are parallel and they're perfectly aligned, let's say, right? Are we talking about the distance between the ropes? What's in between there? Space? We've never talked about the location of the rope. Because, again, we always treat it as energy, and energy is this fuzzy thing that doesn't have location. It's not matter. And so what is that? So we never had the word exist in the context of something like light. Like saying, does light exist? Well, yeah, light exists. What did you mean by that? Well, I don't know what I meant by that. So...
Well, I think the tricky part is...
it's tricky.
Because the other day you were talking about exists, for example, God exists, as in there's distance between his chest and mine.
Yeah.
But when you're talking about the rope, my chest is made of the rope.
Well, your chest is also made of atoms, for that matter.
But you can't really... How do you say that there's distance between my chest and the thread? you know, which part of the thread is
And that brings up that other point that I made last time as well, and that's that, you know, under the rope model, you get this irony, this complete irony, where if, you know, we always talked about the distance, not the length, but the distance between two atoms, right? And we said, well, you know, there's, I don't know, 1 meter between these two atoms, and we can all understand that. And under the rope model, since all atoms are interconnected by a rope, the length of the rope is distance. Distance becomes the length of the rope. So I always criticize the mathematicians because they say that length and distance are synonyms. I'm saying no, they're not. Distance is what is between objects. Length is what is within the ends of an object. And now I have to backtrack under the rope model because distance becomes distance becomes length, and length becomes rope. And now let's take that one step further. If we have the length of the rope, right, and that's distance, right, and now we're going to define what? We're going to define the word location. And what is location? Location is the set of distances from one object to all the rest in the universe. Okay, so now we have this rope. Can we talk about its location? One rope, just one strand of rope that goes from one atom to another, right? Can we talk about its location vis-a-vis the rest of the matter in the universe? Well, again, we've never pondered this because the rope is the first one to bring these types of questions up. And so if you can't define the word exist for the rope, you can't say the rope exists because we don't have location for the rope, which because we don't have distance for the rope between ropes. I don't know if that makes any sense to say that, you know, that there's a distance between the ropes. Maybe you could do that. But if there is no location for the rope, then the definition that we use under the rope model, or rope hypothesis, the definition of exist, which is object plus location, you know, it doesn't apply to the rope. And so you can't talk about the existence of the rope, and if you can't talk about the existence of the rope, you can't say the rope exists scientifically. Now, until we have a better definition of the word exist, or somehow incorporate the rope within, you know, object plus location.
Well, let's go down the checklist. The first question is the thread an object?
Well, yeah. The thread and the rope are objects. The word object, both the thread and the rope, pass with flying colors. Okay. What it can't pass very well is the word...
One thing at a time. Next question is...
Can't pass distance.
Does it have location?
And this is the question.
Does the thread have location?
In order to have location, we're going to follow the definition, and there's got to be distance. And the distance has to be at least, I think it would have to be from the rope to all other objects in the universe, not only atoms, but other ropes, I would think, right? So we would have to consider all the ropes in the universe to talk about distance to the rope, location and distance, both words, right? And that's where it gets a little tricky, but I guess you could do that. You could say, look, if I got a strip of rope, here I have a strip of rope, right? And it holds two atoms. I keep getting off center today. It holds two atoms, right? My hands. And if there's another rope next to it, parallel to it, I guess you can establish a distance between the two ropes. And then you can say, yeah, the rope has distance with respect to not only other ropes, but to every bit of matter in the universe. And so this chunk of rope has location. You could also ask, you know, to pinpoint one location upon the rope, even though it's made of a single piece, you know, the thread is. And then you can start from there and say, well, if it's got distance, now you have the set of distances, you have location. Now you can use the word exist and say, well, yeah, the rope exists because it does have distance and location. And only under that format or that context can you talk about the existence of the rope. Use the word exist in terms of the rope. But again, it's off the ordinary speech by a mile, because in ordinary speech we say even love exists. And in science, love does not exist. No concept exists. There is no love in science.
Here's the weird question of the day, coming from yours truly. If we have a lamp here, right?
But we do.
If this lamp were the only object in the universe, would you say that it has location?
No.
So
because we have no distance to begin with.
Thus, can we say that if the thread, assuming there are no other universes with other chunks of thread, assuming that there's only our thread, and it's the only thing in the universe, it would have no location.
Yeah, and again, we have to distinguish. We have
Except
to
from itself.
Right. Right. Exactly, and that's the key part. Some people say, "Well, does the thread exist?" If we open up all the atoms, we untie all the atoms, all the neutrons, and all the ropes, and we just have the single thread, which is what underlies the rope hypothesis. If you just look at that thread, you know, it has no location unless there's another thread out there, another universe, but it has no location by itself. And all you can say is that one side of the thread, that's on this side, let's assume it's a circle. You know, let's see if I can do it with this. Let's say that's the thread, right? That's the single thread.
Don't use the rope for that. It confuses people.
Yeah, it's think of it as a thread, not as a rope, okay? So it's a single thread, okay, all the way around. And maybe I should get next time some thread.
Use this mouse cable.
So that's a thread, right? So there is distance from this part of the thread to that part of the thread. And of course, this would also move, so you can talk about motion. What are you talking about? You're saying that this location here, which is distance from every other point here, is moving with respect to all the others. So you can talk about motion, you can talk about location, and you can talk about distance. And under that context, right, you can say that this part of the thread exists, not that the whole thread exists.
So weird.
So again, you get into all these weird questions with the rope model, and that's where people need to put their brains and try to see if we can figure out good definitions for that part of the talk. And again, I don't think that in any way undermines the rope model, because the rope model is really for light. It's how the atoms are constructed, why gravity works the way it does. You know, it explains all that. Now, when you get into the nitty-gritty, if you want to say, well, what if I untie all the atoms, all the neutrons, etc., and you stretch it all out and you have this single thread out there, well, now we're talking about something that it's better left for a couple beers at the bar and not really for a scientific presentation. Okay. Anyways, that's my take on that.
How could someone improve their basics in physics? Like what basic things, or more specifically, what mental exercises would you recommend to get someone get better at visualizing or getting better at doing physics?
Well, that's one of the things I'm working on lately, and that is the foundations of physics. I've got a couple of videos which I've uploaded now, which were simply tidbits. I call them vidbits. Little chunks of some of these discussions here, where I try to build the foundations of physics. And I think a person who wants to understand physics, at least my version of physics, is that you need to really go to the nitty-gritty. You need to know what these words mean, the foundations. You need to know what an object is. You need to know what distance is, what location is, what motion is. You need to know all these words. You need to understand them. And that forms your foundations. Then you can build upon them because you got a solid foundation. But you know, one of the things you'll find, especially in high school and college, that there are no definitions. Look at the textbooks of physics, and they don't start saying, look, physics is about object. You need an object to do physics. They don't tell you that. And of course, because they don't tell you that, they don't define the word object. And so they start directly into mass or force. And you say, well, how do we jump to force? Force of what? You know? And if you look at the first few pages of almost every introductory physics book, they start at, you know, mass, force, acceleration. They don't even tell you what motion is. I mean, if they would start at least say, look, this is motion, now we're going to talk about acceleration, then at least there's a flow from square one. But that square one is always missing. And so they go directly to acceleration, assume that you know what motion is. And you look it up in the dictionary, it says change. And change is motion, motion is change. They're synonyms, so you still haven't understood what motion is. So there are no definitions. I think that's what a student needs to learn first, the foundations. Get solid on your foundations, on the wording. Understand them well, then you can build upon them, and then you can understand and explain, right?
Why are normal definitions not sufficient for science?
Well, because they're very loosely defined. First of all, I don't think they were defined by physicists. That's the first one. Who knows who defined some of these words? I mean, if you look at the word object, certainly no physicist in the history of life on Earth defined the word object formally. Even though I'll take that back. I know that, I'm not sure if it was Euclid. I think Euclid. Yeah, Euclid has a definition. And there's another Greek, and I don't think it's Aristotle. But there's two definitions out there from the Greeks. And they're pretty much the same as mine. You know, they say it's form. But the problem here is that, so I didn't really invent the definition. I want you to know that. But this is the issue. I'm the guy who recognizes that that's an important definition. No one ever paid any attention to what Euclid or Aristotle said. Yeah, they said, oh, he says it's form. They just kept going. Nobody said, well, is an object form? Is it shape? Is that what an object is? And nobody has really pinpointed that in physics. And I'm sure that the first question you should ask any mathematical physicist, if we can call them physicists, is, do we need an object to do physics? Can we do physics without any object whatsoever? We only had vacuum out there, you know, nothing. Could we do physics? And I'm sure that if you want to have some phenomenon occurring out there, you need an object. And if you need an object in physics, you absolutely need an object, then you have to start by defining what an object is. You would think that that's the first step in physics. Number one, first step in physics, define the word object because you need objects in physics. No one in the last 10,000 years defined the word object, thing, entity, whatever you want to call it. These are all synonyms for the purposes of physics. And the two guys that did, you know, I know because I've seen that. I got to look that up, but I'm sure Euclid defined it and someone else, some other Greek. And they defined it like, you know, they put it in there as a one-liner, very short one, like object is form or something like that. And then they just left it there and it was buried by time. And so nobody paid attention to that. And to this day, that's not the definition you'll find in the dictionary. In the dictionary, you find see, touch. That's the criterion. You got to see or touch the object for it to be an object. If you don't see or touch it, it's not an object. So, you know, if you can't see the star on the other side of the universe, the word star is not an object because you can't see it or touch it.
Well, again, the question is, to be more specific, why are normal definitions not sufficient for science? Like, where would you come into troubles if you defined it like willy-nilly?
Well,
like
again,
motion,
and again, let's look at those first few words that I think are critical. The word object. If you use the see-touch definition instead of the shape, right?
For example, if I gave a presentation and I started off defining object as that which you can see and touch, and then I went on to explain something about objects.
Well, do we touch a magnetic field? Do we touch light? Some people will say yes, and some people will say no. That's the first part. So you're going to have opinions. Did you really touch the magnetic field? Or did the magnetic field go through? Did you touch a neutrino? Because neutrinos interact poorly with matter. So you can't really tell. We've been trying to touch these neutrinos. We can't touch them. And so the question is a neutrino an object? Well, we haven't touched one yet, but when we do, it becomes an object. Well, I thought a neutrino was an object because it's a particle that we're trying to touch. So it's got to be an object before we touch it. We can't say, well, I'm going to see if I can touch it. Until I do, it's not an object. Then what are you running an experiment trying to touch a particle that is not yet an object? It's not a particle until you touch it. So this is the part. You got a circular thing there. You're running an experiment. You haven't even done your homework on the blackboard. And that's the issue. The issue is that definitions are critical if you're going to go out there and do something. If you call space and you say, well, space is a physical object. Well, can you touch space? Can you see space? I mean, if we remove all the matter in the universe, can I touch or see space if I'm the only matter there, you know, the only living thing floating in space?
That's actually something that
Can I touch it or can I see it? I don't know. You tell me. Can you see space without any objects? Without any contrast provided by objects?
That's something that I've caught, that I used to wonder about when they say, you know, space is curved. I always wonder why astronauts didn't splatter into space.
Right, and that's an important issue.
Or
Not
why,
not only an astronaut, but we sent probes to Mars.
Or why Australia doesn't get crushed by space when when the marble's rolling around.
Yeah,
Assuming Australia is down.
I have a little picture in my website where I'm squashed by the Earth. I assume the Earth rolls around space because it's in contact with space, because if space is a gravity well, it's preventing the Earth from moving out, we should be squashed between the Earth and space. You know, and I've got a picture on that. And so, you know, I don't know if you can do that, if you can come up with an idea where you can say, well, you know, space is warped, Earth pushes up against space, cannot leave the solar system because space is warped, but here I'm between the Earth and space and I'm not being squashed. So we got a serious problem there with their logic, okay? Anyways, we'll see you tomorrow, and again, get your papers ready for the conference if you're going to the conference, and hopefully someone else either challenges me or comes up with a parallel theory on polarization. It's an important topic because polarization will destroy quantum mechanics. By its very nature, you can't do it with particles. And so it's a good point to harp on, you know. We'll see you tomorrow, guys. Bye-bye.